It's great to be back at GopherCon. Hope everyone's having a good time. When I actually proposed this talk, I did not think it was going to be the conference finale, so don't get your expectations too high, but I hope you will find it interesting. As you can see from the slide, I'm going to be talking about range over function types. This is a new Go language feature that will be available in the upcoming 123 release. I'm going to explain why we're adding this new feature, what exactly it is, and how to use it. First question is, what problem are we trying to solve? Why are we doing this? Since Go 118, we've had the ability to write new generic container types in Go. For example, let's consider this very simple set type. Set is a generic type implemented on top of a map. Naturally, a set type has a way to add elements and a way to check whether elements are present. The details here don't matter for this talk. And we'll want a way to make a union of two sets, and so forth. And by the way, I'm not claiming this is the best way to write a set type. It's just an example for the talk. Let's look at the implementation of the union function for a minute. In order to compute the union of two sets, we need a way to get all the elements that are in each set. In this code, we're using a for range statement over an unexported field of the set type. Of course, that only works if the union function is defined in the set package. And, of course, there are lots of reasons why someone might want to loop over all the elements in a set. Set package has to provide some way for its users to do that. How should that work? One approach is to provide a set method that takes a function, and to call that function with every element in the set. I'm going to call this push, because the set pushes every value to the function. In this case, if the function returns false, we stop calling it. In the Go standard library, we see this general pattern used for cases like the sync map range method, the flag visit function, and the file path walk function. But it's just a general pattern. As it happens, none of those three examples work quite the same way. This is what it looks like to use the push method to print all the elements of the set. You call push with a function that does what you want with the element. Another approach to looping over the elements of a set is to return a function. Each time the function is called, it will return a value from the set, along with a Boolean that reports whether the value is valid. The Boolean result will be false when the loop has gone through all the elements. In this case, we also need a stop function that can be called when no more values are needed, if you don't want to go through all the elements. Nothing in the standard library works exactly this way, although both runtime.callerFrames and reflect.value.mapRange are similar. They, however, return values with methods rather than returning functions directly. For set, we're going to implement this approach using a pair of channels, one for values in the set and one to tell the iteration to stop returning values. This is the Go routine that sends values on the channel. Exact details don't matter here, so don't worry if you aren't following this code. The existence of this Go routine is why we need to use a stop function to make sure the Go routine exits when no more values are needed. And here are the two functions that we're going to return. The next function returns an element from the set by reading from the channel, and the stop function tells the Go routine to exit by closing the stop channel. This is what it looks like to use the pull method to print all the elements of the set. You call pull to get a function, and you repeatedly call that function in a for loop. We've now seen two different approaches to looping over all the elements of a set. Different Go packages use these approaches and several others. That means that when you start using a new Go container package, you may have to learn a new looping mechanism. It also means we can't write one function that works with several different types of containers, as the container types will handle looping differently. So we want to improve the Go ecosystem by developing standard approaches for looping over containers. This is, of course, an issue that arises in many programming languages. The popular Design Patterns book, first published in 1995, describes this as the iterator pattern. An iterator provides a way to access the elements of an aggregate object sequentially without exposing its underlying representation. Like many ideas in programming, iterators date back to Barbara Lyskov's CLUE language, which was developed during the 1970s. Today, many popular languages provide iterators one way or another, including C++, Java, JavaScript, Python, Rust. However, Go, at least as of the current 122 version, does not. And by the way, what this quote calls an aggregate object is what I've been calling a container. An aggregate object, or container, is just a value that holds other values, like the set type that we've been discussing. As we all know, Go does have container types that are built into the language, slices, arrays, maps. And it does have a way to access the elements of those values without exposing the underlying representation. The for range statement. The for range statement works for Go's built-in container types, and also for other types listed on the slide. The for range statement is iteration, but it is not iterators, as they appear in today's popular languages. For example, there is no way to use for range to read two containers in parallel. And of course, there is no standard way to use for range to read a user-defined container like the set type we were just looking at. This suggests two different approaches for looping over all the elements of a container. We could find some way to extend the for range statement to work with user-defined container types like set. Or we could find some way to define general-purpose iterators in Go. Why don't we have both? In Go 123, we're going to extend the for range statement to support ranging over function types. We'll soon see how this helps loop over user-defined containers. We're also going to add standard library, types, and functions to support using function types as iterators. A standard definition of iterators will let us write functions that work smoothly with different container types. The for range statement isn't going to support any arbitrary function type. It's going to support ranging over functions that take a single argument. The single argument must itself be a function that takes 0 to 2 arguments and returns a bool. By convention, we call that the yield function. When we speak of an iterator in Go, we mean a function with one of these three types. As we'll discuss later, there is another kind of iterator in the standard library, a pull iterator. When it is necessary to distinguish between standard iterators and pull iterators, we call the standard iterators push iterators. That is because, as you will see, they push out a sequence of values by calling a yield function. To make iterators easier to use, the new standard library package iter defines two types, seek and seek2. These are names for the iterator function types, the types that can be used with the for range statement. The name seek is short for sequence, as iterators loop through a sequence of values. The difference between seek and seek2 is just that seek2 is a sequence of pairs, such as a key and a value, from a map. In this talk, I'll focus on seek for simplicity, but most of what I say covers seek2 as well. It's easiest to explain how iterators work with an example. Here, the set method all returns a function. The return type of all is iter.seek of e, so we know that this method returns an iterator. The iterator function itself, which is returned by all, takes another function, the yield function, as an argument. The iterator calls the yield function with every value in the set. In this case, the iterator, the function returned by set.all, is a lot like the set.push function we saw earlier. This shows how iterators work. For some sequence of values, they call a yield function with each value in the sequence. If the yield function returns false, no more values are needed, and the iterator can just return, doing any cleanup that may be required. If the yield function never returns false, the iterator can just return after calling yield with all the values in the sequence. Now, I want to acknowledge that the first time you see one of these, your first reaction is, okay, there's a lot of functions flying around here. And you're not wrong. I want to focus on two things. The first is that once you get past the first line of the function's code, the actual implementation of the iterator is pretty simple. Call yield with every element of the set, stopping if yield returns false. Second point is that using this is really easy. You call s.all to get an iterator, and then you use forRange to loop over all the elements in S. The forRange statement supports any iterator, and this shows how easy that is to use. In this kind of code, s.all is a method that returns a function. We are calling s.all and then using forRange to range over the function that it returns. In this example, we could have made set.all be an iterator function itself rather than having it return an iterator function. However, in some cases, for some container types or any other type, that won't work, such as if the function that returns the iterator needs to take an argument, or if it needs to do some setup work. As a matter of convention, we encourage all container types to provide an all method that returns an iterator, so that programmers don't have to remember whether to range over all directly or whether to call all to get a value that they can range over. Now, if you think about it, you'll see the compiler must be adjusting the loop to create a yield function to pass to the iterator returned by s.all. There's a fair bit of complexity in the Go compiler and runtime to make this efficient and to correctly handle things like break or panic in the loop. I'm not going to cover any of that in this talk. Fortunately, the implementation details are not important when it comes to actually using this feature. We've now seen how to use iterators in a forRange loop, but you'll recall that earlier I said that one use of iterators was to read two containers in parallel. How do we do that? The answer is that we use a different kind of iterator, a pull iterator. We've seen that a standard iterator, also known as a push iterator, is a function that takes a yield function as an argument and pushes each value in a sequence by calling the yield function. A pull iterator works the other way around. It is a function that is written such that each time you call it, it returns the next value in the sequence. I'll repeat the difference between the two types of iterators to help you remember. A push iterator pushes each value in a sequence to a yield function. Push iterators are standard iterators in the Go standard library and are supported directly by the forRange statement. A pull iterator works the other way around. Each time you call a pull iterator, it pulls another value from a sequence and returns it. Pull iterators are not supported directly by the forRange statement. However, it's straightforward to write an ordinary for statement that loops through a pull iterator. In fact, we saw an example earlier when we looked at using the set.pull method. You could write a pull iterator yourself, but normally you don't have to. The new standard library function iter.pull takes a standard iterator, that is to say, a function that is a push iterator, and returns a pair of functions. The first is a pull iterator, a function that returns the next value in the sequence each time it is called. The second is a stop function that should be called when we are done with the pull iterator. This is like the set.pull method we saw earlier. The function that I've named next, the pull iterator, returns a value and a Boolean that reports whether that value is valid. The Boolean will be false at the end of the sequence. Iter.pull returns a stop function in case we don't read through the sequence to the end. In the general case, the push iterator, it is the argument to iter.pull, may start Go routines or build new data structures that need to be cleaned up when iteration is complete. The push iterator will do any cleanup when the yield function returns false, meaning that no more values are required. When used with a forRange statement, the forRange statement will ensure that if the loop exits early, through a break statement or for any other reason, then the yield function will return false. With a pull iterator, on the other hand, there is no way to force the yield function to return false, so the stop function is needed. Another way to say this is that calling the stop function will cause the yield function to return false when it is called by the push iterator. Strictly speaking, you don't need to call the stop function if the pull iterator returns false to indicate it has reached the end of the sequence, but it's usually simpler to just always call it. Oh, I skipped ahead somehow. All right, doesn't matter. I know this can be confusing when you see it for the first time, so I'll go over the differences between the two kinds of iterators again. Push iterators work with for range and are easy to use. Push iterators are the standard iterator type and are named types in the iter package. Pull iterators, on the other hand, are more flexible because you can call them whenever you need a value, rather than having to get all the values via for range. However, they are harder to use because you have to check the Boolean OK result on each call, and because you have to make sure to call the stop function at the right time. Here is an example of using pull iterators to walk through two sequences in parallel. This function reports whether two arbitrary sequences contain the same elements in the same order. The code is a bit packed, but you can see we call iter.pull to convert the two push iterators, S1 and S2, into pull iterators. We use defer statements to make sure the pull iterators are stopped when we are done with them. Then we loop, calling the pull iterators to retrieve values. If the first sequence is done, we return true if the second sequence is also done, or false if it isn't. If the values are different, we return false. Then we loop to pull in the next two values. As with push iterators, there is some complexity in the Go runtime to make pull iterators efficient, but this does not affect code. It actually uses the iter.pull function. At this point, you know everything there is to know about range over function types and about iterators. I hope you enjoy using them. Still, there are a few more things worth mentioning. An advantage of a standard definition of iterators is the ability to write standard functions that use them. For example, here's a function that filters a sequence of values, returning a new sequence. This filter function takes an iterator as an argument, and it returns a new iterator. The other argument to filter is a filter function that decides which values should be in the new iterator that filter returns. As with the earlier example, the function signatures look complicated when you first see them. Once you get past the signatures, the implementation is straightforward. We range over the input iterator, we check the filter function, and we call yield with the values that should go into the output iterator. As an example of how convenient the push iterator can be to loop over a container type, let's consider this simple binary tree type. I won't show the code to insert values into the tree, but naturally there should be some way to range over all the values in the tree. By convention, the all method returns an iterator over the values. The iterator itself is the all values method. In this case, it's simpler for the push function, which we'll see on the next slide, to return a Boolean. This does force us to separate the all values method and the push method. The all values method just calls the push method and ignores the Boolean result. Here is the implementation of the iterator. It uses recursion to walk over the whole tree, calling yield on each element. If the yield function returns false, the iterator returns false all the way up the stack. Otherwise, it just returns once the iteration is complete. This shows how straightforward it is to use this iterator approach to loop over even complex data structures. There is no need to maintain a separate stack to record the position within the tree. We can just use the goroutine call stack to do that for us. Also new in the upcoming Go 123 release are functions in the slices and maps package that work with iterators. These are some of the new functions in the slices package. I won't go through all of them, but all and values are functions that return iterators over the elements of the slice. Collect fetches the values out of an iterator and returns a slice of those values. And these are some of the new functions in the maps package. All keys and values return iterators over the map contents. Collect fetches the keys and values out of an iterator and returns a new map. Here's an example of how you might use these functions along with the filter function that I showed earlier. This function takes a map from int to string and returns a slice holding just the values in the map that are longer than some argument n. The maps.values function Down at the bottom, returns an iterator over the values in M. Filter reads that iterator and returns a new iterator that only contains the long strings using this int long predicate defined in the function. Slices.collect reads from that iterator into a new slice, and then we return it. Of course, you could write a loop to do this easily enough, and in many cases, a loop will be clearer. I don't want to encourage everybody to write code in this style all the time. That said, the advantage of using iterators is that this kind of function works the same way with any sequence. In this example, notice how filter is using a map as an input and a slice as an output without having to change the code in filter at all. Although most of the examples I've shown have involved containers, iterators are flexible. Consider this simple code, which doesn't use iterators, to loop over the lines in a byte slice. This is easy to write and fairly efficient. However, bytes.split does allocate and return a slice of byte slices to hold the lines. The garbage collector will have to do a bit of work to eventually free that slice. Here is a function that returns an iterator over the lines of some byte slice. After the usual iterator signature, the function is pretty simple. We keep picking lines out of the data until there's nothing left, and we pass each line to the yield function. Now our code to loop over the lines of a byte slice looks like this. This is just as easy to write as the earlier code, and it's a bit more efficient because it doesn't have to allocate a slice of byte slices. For my final example, I'm just going to mention you don't have to use a push iterator in a range statement. You may remember this function I showed earlier in the talk. It prints out each element of a slice, of a set. Here's another way to print all the elements of a set. Call s.all to get an iterator, then pass in a handwritten yield function. This yield function just prints a value and returns true. Note that there are two function calls here. We call s.all to get an iterator, which is itself a function, and we call that function with our handwritten yield function. There's no particular reason to write code this way. This is just an example to show the yield function isn't magic. It can be any function you like. Before closing, I want to mention that every Go module specifies the language version that it uses. That means that in order to use new language features, like the ones I've been talking about, in an existing module, you may need to update that version. This is true for all new language features. It's not something specific to range over function types. This slide shows 3 ways to set the language version. You don't have to memorize these. They're easy enough to look up. As long as you're aware, you have to actually do it. Go 123 release is scheduled to come out next month, and then you'll be able to use all the new functionality I've discussed. Thanks for listening. Thanks to everyone who uses Go. Thanks especially to all the many people who worked so hard to make this a great GopherCon. Thank you.